final. Now I think everything should be perfect. Thank you very much for the introduction, and it's really a great pleasure to be here and to talk about quantum computing, building up a new computing paradigm. And I would like to start, as you all know, of course, quantum computing is really a completely new and radically approach to computing. And it's not something which is kind of right now falling from the sky, as some may believe, but there has been, of course, a lot of hard work behind to bring it to the stage where it is right now. A lot of ideas and research and development which have gone into quantum computing, and also in the future has to continue going into quantum computing. And therefore, I would like to briefly share also a bit of the history where things have started with, of course, the quantum physics, the EPR paradox and Bell's inequality, but then a lot of development and physics insights had to be created. And then the idea has been brought by this brilliant idea of quantum computing. Actually, Richard Feynman had at a conference which was co-hosted by MIT and IBM in 1980. And since then, a lot of work has went into quantum computing, from creating the concept, creating the idea, to figuring out what is needed for building true quantum bits, how to control these quantum bits, what are error correction codes which can be used, then circuit quantum electrodynamics, which has been demonstrated, and then also kind of qubits, which have been demonstrated in many physical implementations. And we actually focus on superconducting qubits. So the transmon has been demonstrated, and many more of those things, until in 2015, we for the first time were able to demonstrate a 5-qubit chip, which made be available through the IBM Cloud in 2016. And since then, a lot of new things have happened, and I would like to lead you through the new things which are currently going on, and also what is coming in the future. So this is how a typical quantum computing lab looks like. You have the quantum computer, which is sitting in the fridge, which is behind this white cylinder here at the left-hand side. And then you see all these racks and these blue frames of electronic instruments which are needed. And you can imagine that also scaling up the number of qubits by using this type of equipment is kind of expensive. So a lot of work also goes into the electronics in order to make quantum computing scalable with time. But this was a lab in 2016 when we for the first time launched quantum computing into the cloud. And this was really a very inspiring moment, because at that time we were also thinking about, is it worth launching this into the cloud or just continuing developing the hardware development? And we've decided then to really make this launch, make the 5-qubit processor, which was at that time, of course, also very tiny, accessible to the quantum researchers. And this, of course, led to many other things, because suddenly we also need to start developing the quantum computing framework, the software. We provided also education material and a lot of other things in order to make people familiar and also to accelerate the research and educate and train people. So since then, as you see, when we launched it, and you see here a lot of white points popping up across the world, and this actually demonstrates the increase of the usage of the quantum computers, which are now accessible. And you see a lot of us happened, and a lot of users of quantum computing across all the world. You can see here, even at the North Pole, there were people using quantum computers and starting off very, very soon after we launched them. And today, we see actually the transition from the lab to the quantum computing data center. So we have done a lot of work of engineering these lab instruments into quantum computers, which are engineered for robustness, rigidity, and also continuous commercial use, for having a very high availability for operation. So you see that today we actually have about 38 quantum computers which are deployed in the cloud, and more than 300,000 registered users were actually using those quantum computers. We created also since 2017 a quantum network where we work together with many partners, also with partners in Germany, in particular also the Bundeswehr University in Munich. And over there have been more than 780 billion of quantum circuits have been run on the quantum computers. A lot of research and development has resulted out of this, with more than 500 scientific papers, and also a large open source community has been set up since then. And so you see that there's a lot of dynamics in the system and a lot of new activities which are ongoing. So when we see what's coming next, or where are we? So if we look at the quantum technology which we have built, so you see here the quantum processors. We are using superconducting qubits. And you see here the two quantum processors which are currently mainly used. This is a 27 qubit processor Falcon. And then in 2020, last year in August, we actually have demonstrated the 65 qubit chip, which is called Hummingbird. And for each of those generations, new technology development come in order to kind of break a certain barrier which hampers going to the next level. So when we look at the Falcon, then here you see an optimized lattice of the qubits. This is important for error correction. Also important is to increase the yield of quantum computers of qubits. And then when we go to the Hummingbird, then there is also how can we make these things more scalable, the readout in particular, because if you have 65 qubits and if you increase furthermore, you need to make sure that you can read and control the quantum bits in a scalable manner. And then this year, actually, we plan towards the end of the year to demonstrate a 127 qubit chip called Eagle. And here we break the 100 qubit barrier with new technology coming in, which is technology in the area of packaging and control, of increasing the density of the qubits, reducing the crosstalk, and several other key technologies which we bring in order to break this 100 qubit barrier. Next year, we plan 433 quantum bits. And again, also here, there are further technical key enhancements we bring in, further miniaturization of components, and also more efficient quantum bit control. And the next family, which actually end of 2023, is then the Condor family. And here we want to break the 1,000 qubit barrier, which is a significant barrier of scaling up, where further integration and also further breakthroughs in the physics are needed. And in the physics, because we need to further increase the fidelity, this means the quality of the quantum bits, because important is the performance of quantum computing can only be improved if we not only increase the number of qubits, but also increase the quality of the qubits, because both of these components working together will increase the complexity of calculations we can do on quantum computers. And of course, we also think beyond this to prepare a path of what is needed from a technology point of view to go beyond the 1,000 qubit and towards the 1 million of qubit to build larger systems. And for this, we already start to build new infrastructure like new fridges, etc. And of course, also continue to work on the quantum error correction. So that's important to scaling up the technology. And this is actually similar to the semiconductor technology, because also in semiconductor technology, we needed to scale up. And if you look back, like in the early 70s, then the integrated circuits had about 2,000 transistors. And today they have like 40 billion of transistors. So you see also in the last 40 years, a lot of improvements has been made. And of course, this is also needed for the future of the quantum computing. Why are quantum computers of interest? Because of the problems they are able to solve in the future, which classical computers cannot solve. And you all know the example of factorization. But of course, there are many more of those interesting examples of simulating quantum chemistry, quantum systems in physics and chemistry, material science. And material science is one important issue in many applications if we can improve materials, we can also bring a lot of innovation to the industry. Algebraic problems in machine learning, differential equations in factoring, but also for database search. Quantum computers have a potential to create value in the future, whether this is for quantum Monte Carlo simulations or optimization problems like routing, supply chain graph problems, and others. So quantum computers are really intended to provide a new path to solve some of the hardest business problems, and of course also in science. So here are a bit more a further example. I don't want to go into detail, but material simulation and discovery, quantum chemistry simulation, discover new catalysts, understand reaction rates and pathways to find new materials, but also in high energy physics and simulation. You can also apply them to linear systems solvers. This may be for high precision partial differential equations, but also matrix inversion or network conductivity problems. So many more, also in particular optimization problems, are actually very interesting for industry, whether this is for finance industry, but also as discussed here during the day, also for supply chain. So there is a lot of interesting application areas where quantum computers can be of potential value. And this is currently strongly investigated by industry, research, science, etc. So what I wanted to show here is that over the last 6 years, a lot of activity has come in, and you see here many of our partners, and in particular, of course, also the Bundeswehr University in Munich, who is also a partner of the network, and all these are actually accessing the our quantum computers and are developing new types of applications of quantum computing. Oops, let's go to the next chart. Somehow it's okay. So what's important for the future is, of course, also that using quantum computers becomes easier, and that we develop kind of a frictionless use of quantum computers. And this means we also need to work on the software that developers, as they use today's classical tools, are also enabled in the future to use similar tools, similar languages, and the same code for solving their problem. This, of course, means that we have to kind of bridge that gap of developing the software, which has been developed for classical computers over many years, now in very short time. And this is the development roadmap which we have set up to develop the right tools for bringing quantum computers to software developers, to applications. And we have categorized this in 3 levels of the kernel developers, the algorithm developers, and the model developers, that if you are at the top of the stack, it should be very easy for you to use your typical classical tools which you use today, but kind of plug in the quantum services for natural sciences, finance, optimization, machine learning, etc. So I have to speed up, and before I want to end, I actually also want to show that quantum education and enablement is at our heart. And in the last 6 years, we have also put a lot of effort into enabling people to learn about quantum computing and to use quantum computers by making quantum computers freely accessible to some extent. So access to open systems, the open access is important, but also open source. So developing a open source software kit like Qiskit, which is available on GitHub to everyone. And also, of course, in the training and education on quantum computing, we have provided a lot of education opportunities which can be used very easily, like Qiskit YouTube channel, or also with a researchers program or educators program, a Qiskit textbook with very easy examples and easy access to learning about quantum computers, and also a lot of hackathons or summer schools where interested people can apply and join for learning about quantum computers. So you see, just want to finish actually with this highlight also from the 15th of June, where for the first time we have actually brought a quantum computer to Germany, and this was the inauguration of the IBM Quantum System 1, which is in collaboration with Fraunhofer Institute here. And this is now physically sitting in Germany and also complies with the the full data sovereignty according to the European law. And so with this, I actually would like to stop and say thank you very much for giving me the opportunity. It's a great journey we are on, and I'm very happy also that we are here in very, very close collaboration with many German partners. And in particular, of course, also the Bundeswehr University in Munich. Thank you very much.